So, good morning. Good morning. I want to give a short overview today of our end-to-end MLOps pipeline that we built at BSH. But before we dive into the technical details, let's first answer the most important question. What is MLOps and why do we need it? And to answer this question, I want to go back some decades and first answer this question. What is DevOps and why is it omnipresent in software engineering? So who of you already know what DevOps is? Okay, fine. And who of you know what MLOps is and how they relate to each other? Oh, that's much less. Yeah. So just give me a short refresher. DevOps is all about reproducibility, having a shorter time to market for the product and hopefully also consistent quality. And essentially you use three pillars. You have first a continuous integration, so you have one artifact, in this case the version code that you use to keep track of what is out there and on which version of the code people work together. This also avoids the problem that if somebody gets sick in the team or is on holiday, that you always know where the code is and not on maybe the local laptop of this person in the worst case, which happens sometimes. So it's all about teamwork. It's not only about technology, it's the technology used to improve teamwork. The next stage then is you want to keep track of the quality of your code by writing and running automated tests, and also automate the deployment process. So essentially regularly checking the status of the code before the next iteration goes into production. And of course the last stage is then you hand this over into the running stage where you do some monitoring to essentially observe if your application runs as intended, so like performance metrics, robustness metrics, also checking if the underlying infrastructure is is still stable. Now the question is, how does this relate to MLOps? And I would say MLOps is just an extension of DevOps. So instead of the one artifact, which is the version code from DevOps, you now have three artifacts ideally. So you also have to keep track of which model is running in production. And also in the case of model training, you don't create the code, you train the model. So you also need to do experiment tracking. Therefore, having a version number of the different stages of the models you use is of a big advantage. And ideally, but from our experience, that's something that is not mature enough. That's something industry have to find better solutions, is also having a snapshot of the version data. So that only if you have all these three artifacts, you have complete reproducibility and can go back from a running model that maybe does some false predictions back to doing a root cause analysis by understanding with which data it has been trained, which model was it, and also which code was packaged around it to essentially communicate with the outside world. Then the next stage is again similar. You run still the traditional tests from software development because you still have some parts that are software. But in addition to that, you also want to know how your model behaves. So you have specialized tests, maybe some edge cases where you know what should be the predictions, so that you also can do some regression tests. If you switch out the model, does it still do the predictions as the previous generations for the known data points? And then in running, it's again keeping the traditional monitorings from DevOps, and in addition to that, now checking how does the model behave. So is there some degradation? Maybe the outside world has changed, so you might have some concept drift or data drift. So the result, as I said, is you have faster rollouts, so faster time to market by using such a pipeline, and you have reproducible behavior. Okay, now we can go more into detail. But first, why did we not just buy some ready-made framework out there? Why did we build our own generic pipeline at BSH? Because there are lots of great frameworks out there. So, and in our case especially, we have certain problems we have to deal with. First of all, as we are a large corporation, we have a really heterogeneous landscape of use cases. So we have industrial IoT data, we have our consumer IoT data, we have traditional batch processes, so slow and also already fast-moving data going in the direction of near real-time processing. We have images and natural language processing, sensor data, as I said. So it was clear if you want to avoid that each single use case builds their own pipeline and has to do software development, we need to find some flexible, versatile, but also modular architecture, essentially to give the data scientists tools that let them build their use case specific pipeline out of our bricks that we build. Another thing you have to take into consideration in a large corporation, of course, are the corporate constraints like cybersecurity, data protection on different level. Of course, if it's personal data, GDPR compliance, governance issues in the direction of is it confidential data or several levels of confidentiality. This is all often a problem if you buy a ready-made product that it might be a fantastic product, it just doesn't fit well into your landscape. So what we identified throughout the years is there are several issues. One is the black box issue. You don't have control of the code, over the code. So, and often, unfortunately, more often than not, you run into some brick walls at some point. So it works for a while, but then you get a use case that is slightly different, that has some new requirements. And then you are essentially stuck because it's a black box. You don't understand the underlying technology. And it might even have a plugin system that you can extend it to some point, but often it's really that either you have to build a workaround that is, again, quite takes a lot of time, or you're just hitting a brick wall. So we decided, let's drive it by our use cases, build an evolutionary architecture, so essentially adding modules with each new use case so that it still fulfills the newer use cases. For example, one problem we used two small tools that we had combined, like MLflow and Aporia, and we didn't want to have this one vendor login. So now that we have clarified why we built this generic pipeline, let's finally dig into the details how we built it. The first and most crucial component was a specialized developer environment. Not sure what's your background, but in larger corporations, sometimes you just have these Windows instances that are completely closed, that are more tailor-made for people that do presentations or do word processing. But it's really not meant for this fast-paced community of developers and data scientists that constantly need to install their own tools, constantly need new tools. and need more control over the machine. So that's why we decided create this development environment, which also acts as a foundation to create the code for or to configure the different modules of the pipeline. So it's and to orchestrate it. And you can, of course, also run some small experiments already, do some exploratory analysis, for example. So at the BSH, we call it our data science workplace. Another point was in the consideration of big data. We have lots of, or two main pillars of big data, as I said, industrial IoT and consumer IoT. So we wanted to bring the code to the data so that we don't have to move around the data. So this data science workplace is also running on our AWS cloud, where everything else is also running. So let's start with the first stage. Of course, you need to have some data ingestion. Here we have several, to tackle several requirements like traditional batch, also streaming, and also doing some intermediate storage already. And the best practice we understood after a while is also already in this early stage doing some basic quality checks. So that's, I think, where Sifley comes in from yesterday's talk. You might have heard it's becoming more and more important to check the quality of your data as early as possible, because then you can automate the processes, and also that's one goal we are heading for, is differentiate the use case agnostic data quality checks from the use case specific. So again, it's freeing the data scientists from repetitive work that you can automate. Also, there might be some early stage storage optimizations for later query optimization, like you might have from sensor data millions of small JSONs, and you don't want to store them as a single JSON. You might want to package them already and maybe compress it, put it in a binary format like Parquet, to also save some cost. And then next stage is already the use case specific preparation. Again, you do some transformations, you might do some feature engineering, and now comes in the extended quality checks. So together with the knowledge of the use case, you then add additional checks here, but they are now use case specific. So it's, while this module in the pipeline might be generic, adaptable, configurable, you definitely need someone who does this configuration on a use case specific level. And yeah, in some use cases, you want to do some labeling. So we have some tools where we have some cooperations with vendors. And you might have to hire a team for doing the labeling and also train it. So it's cost intensive. That's something that definitely needs to be improved, going in the direction of state-of-the-art technologies like active learning, or maybe what Jan LeCun proposed, I think 1 or 2 years ago, this self-supervised learning. But as far as I know, it's not yet mature enough to be used in industry. Then we have our training infrastructure, where we do the model selection, training and evaluation, also setting a baseline. And here you can then fire up on demand, depending on the use case, on demand infrastructure. For example, a GPU cluster that is getting fired up during the training and thrown away when the training is done to save cost. We also have Spark clusters for heavy-duty ETL processes. So here we currently use MLflow for experiment tracking and the model version that was mentioned earlier. And optional, this is already for the last stage. I come to this later in more detail. You want to prepare the model monitoring already during the training cycle, because here you know what the expected model behavior should be, and you can set up the configuration for, or you should set up the configuration for the model monitoring that you use later, and hand it over with the rollout then. Then, again, the traditional processes of the DevOps or MLOps pipeline. You automate the testing and deployment. Here you can use any tool you like, Bamboo, Jenkins. We also use the SonarQube for code smells. This is going into the direction of automated retraining. If you get a feedback loop, you could go through this stage again and retrain your models here. Like in traditional DevOps, you have some quality gateways before you do the rollout then. And optionally, and this is quite new, we are in cooperation with our mother company, Bosch. They have a specialized team that is now looking deeper into this quite new tool called TVM or OctoML. It's a specialized compiler that is hardware aware. So you can compile your model without sacrificing performance for a specific hardware. So it's really hard aware. These compilers have to be written for each new hardware, and they are then really aware of the minute intricacies of each hardware, what caching mechanism it has, how many registers, and what else. The big advantage is, especially in our case, that you can essentially train a model once and then roll it out into different target architectures. You can run it in the cloud, where you use some compilation, maybe like TensorRT or TensorFlow Lite. So it's essentially three. Do I have time? Yeah. Three ways you can improve a model. One is on the model itself, but then you sacrifice some performance, some predictive performance, where you can do quantization. So going, for example, from float to 32 to int 8 or int 4 even. That's something that NVIDIA does intensively. But then you have to have this feedback loop and observe how much of the performance you sacrifice. Also, you can prune identify some neurons that are not used, so you could prune those connections and therefore also reduce a little bit of the computational power needed. But this TVM compiler is a different approach. It's not changing the model itself. You'd have to just export your model in a generic format called ONNX. And it's not changing the weights, it's not changing the underlying the underlying functions, the activation functions, and this is all staying the same. It's just compiling it for this hardware. And this is really nice if you want to roll out your models also in embedded devices, as we do in our appliances. So essentially, you can create a fallback system with this. You roll it out into your appliance, and if the connection via Wi-Fi to your big data center is available, you can do the full-fledged prediction with a big model, but you still have the possibility to do some predictions on the device. Yeah, coming to the last stage, running and serving. We have, of course, the traditional monitoring of the application, bug tracking, infrastructure tracking. In our case, it's on the lowest level, it's just CloudWatch from AWS because we run on AWS, but it could be essentially any logging and system. Then we have the post-deployment model monitoring with the behavior tracking, which in our case is Aporia. So we did lots of evaluations, compared several potential candidates, and in our case, Aporia was the sweet spot. It fit quite nice into our infrastructure, and it works more or less good together with MLflow for the versioning. You might also want to add something like a protection for your application, something like guard duty or web application firewall or Grafana to monitor, to do visually. So that's it. Some short outlook about some practical considerations and pitfalls we had observed. As probably most of you have run into this problem that the evaluation of tools is on the one hand necessary, but it's really, really time consuming. So it's extremely important that we do this in a well-structured way. And in order to do this, one mistake we made in the past is that this mix between the short-term and the future demands was not clear enough. And then you are essentially stuck. You can have a list of 100 potential tools, and it's difficult to make a short list of those that you want to use for doing POCs. So that's really one of the crucial parts to really to get your demands right and understand what is necessary now, but also what is necessary in 1 or 3 years. Otherwise, you have to switch out tools too often. And that's really a fine balance. Of course, you don't want to plan for 10 years ahead, but also just solving this one use case doesn't all make sense, because then it's too much effort. Other pitfalls we ran into are, you have to avoid vendor logins, definitely. That's a big problem. Again, coming to this short-sighted view, it's important to avoid expensive migrations, because often it looks like you have now a fast solution that solves your one use case, and then after 1 year you identify, okay, but this doesn't fit in our infrastructure, we have to migrate it and essentially rebuild it from scratch, and then you have paid the price twice at least. So that happens when your due diligence is not done as expired. Then the outlook, what we are still looking into is finding some better tools for data versioning, also data quality automation. We think about a multi-layer stack where you start with the low-level transport quality checks like schema evaluation and validation and enforcement that you could do in Kafka, for example, in the streaming case. Then maybe some levels higher, looking at the domain expertise and building a small rule engine so that the domain experts that create the data, for example, if you are talking about physical processes, the engineers that put some sensors on a machine, they know what kind of data the sensor should deliver, and they could put in these constraints in a kind of rule engine. Then you can also, again, completely automate this process without looking at a specific use case. That's something where we search for better tools. Then model compilation, we want to have a deeper look into also saving more cost, and ideally really train a model only once and deploy it on multiple infrastructures. And one bigger goal we have for the next years is getting more and more into the personalization. That's, I would say, a quite tough task, because as we are producing appliances for households, you could imagine the ideal case would be that your appliances after a while understand what are your wishes, what is your usual behavior, and then you would train tailor-made models and keep them out in the field. And then you, of course, have to have something like a fleet management where you have to keep track of those millions of models that are out in the field. And that's something, we are just thinking about, but it's far from being implemented. Okay, that's all from my side. Thank you very much.